and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit 10, Lesson Number 4, More Polar Calculus. As a reminder, in the last lesson what we did is we took functions where we knew r as a function of theta, so we knew the radius as a function of the angle, and we were able to figure out then the slope of the curve, specifically dy dx, or f prime of x, for a particular theta. And we did this really using what we learned from parametrics. Today, we're going to actually experiment with a whole nother concept in polar calculus. And it can really be summarized by the following. We know what dy dx tells us, right? We know, I don't know where my pen is, there it is. We know that if we've got a curve, even a polar curve, right? Even r equals a function of theta, we know that what dy dx tells us is the slope of that tangent line, right? Almost looked like a tangent line, right? So if I give it a theta, right, if I give it some angle, theta, this quantity tells us the slope of that line. But it still kind of begs an important issue, which is what does dr d theta tell us? What can we do with dr d theta? It seems kind of weird that that didn't link in with dy dx at all, right? What is dr d theta? So that's what we're going to explore in the lesson today. What is dr d theta? What does it tell us? What can we get from it? And I think that you'll find the conclusion of this really, really satisfying. So I'm going to clear out, and let's get investigating. Okay, the first problem is kind of long, and what we're going to do is we're going to take a look at something known as a polar rose. I love this. We're going to get into these more in the next lesson. R equals sine 3 theta. And what I'm going to ask you to do is for this weird angle, pi over 12, whatever, we're going to find the exact value of r and the exact value of dr d theta, and then we're going to graph it on our calculators, and we're going to see whether or not the curve is getting closer or farther, i.e. the distance the curve is it increasing or decreasing at that value of theta? So let's do this together. All right, first let's figure out what r of pi over 12 is. That's pretty easy. It's going to be the sine of 3 times pi over 12. Sorry. Oh, I hate it when I do math and talk at the same time. Let me just get rid of all of that. Let's try that again. It's going to be 3 times pi over 12, which is going to be the sine of pi over 4, which of course is root 3. Oh, you would think I wasn't doing math all day, which is root 2 over 2. Anyway, let me figure out what dr d theta is. Try not to make a mistake. For that, we're going to have to use the chain rule, right? It's going to be 3 times cosine of 3 theta. If I want to figure out what that is, when theta is pi over 12, it's simple enough, right? It's going to be 3 times the cosine. Now, if I put the pi over 12 in for theta and I multiply by 3, we're going to continue to get pi over 4. So that's going to be 3 times root 2 over 2, which is, I guess, 3 times root 2 over 2. All right, so those are our two answers, and they probably don't hold any special significance for you, and I don't think they should hold any special significance for you right now. But let's do this. For the first time, let's pull up our TI-84 Plus. All right, got it up on the screen. Let's check to make sure that we are in polar mode. You never know, so hit our mode button. Check to see if we're in polar. If we're not in polar, change it. All right, let's go to y equals, which is really r equals. Let's clear out any curves that we might have in here. All right, now let's just put in sine 3 theta. So sine 3 theta. Okay. I gave you the window, so let's go into the window. Let's set theta min to be 0. Theta max to be pi. By the way, I know that's a little weird. We'll explore that more in the next lesson. Let's see. I want my x min to be -1. I want my x max to be +1. I want my y min to be -1. I want my y max to be +1. Okay, check my window. Really, just on the angle, really quickly, we just really needed to make sure that we had an angle, theta min, theta max, that included pi over 12, right? Pi over 12 was somewhere in between them, which it is. Okay, let's hit graph. Now obviously it traces out the whole curve, but what we're curious about is what's going on at pi over 12. Pi over 12. So what I'm going to actually do is hit the calculate button on my calculator, and I'm going to go to value. All right. What value does in general is when you put in a value of the independent variable, it will put the cursor at that point in the graph, all right, and it'll tell you what the coordinates are. So if I put pi over 12 in for my value, it puts me right there on the graph. Now what I can see, especially if I paid attention, was that at that point on the graph, the distance the curve is away from the origin is increasing. So the distance from origin is increasing. You could say that the curve is getting farther away. Curve is getting farther away. Now, you might have some sense for why that is. You might even think it's just due to the fact that dr d theta is positive. But we'll see. We'll play around with this some more. Don't worry about it for now. I'm going to clear out the text. Okay, get rid of the calculator. All right, let's go on to part B. Now, in part B and part C, we're going to do exactly the same thing, except we're going to do it for 2 additional angles. So I would like you to do that as well. I'm not going to bring up the graphing calculator again. All right, so that's important, and it's really important that you do that because we're trying to develop a test right now. So pause the video, take up to 10 minutes to figure out r, dr d theta, graph the curve, and figure out whether or not the curve is getting closer or farther away from the origin, likewise whether the distance is increasing or decreasing. Okay, pause the video now. All right, let's go through it. So, our first angle, simple enough. Let's see, we have r of pi over 4. That's going to be the sine of 3 pi over 4, just immediately multiplying by 3. And that's our friend root 2 over 2 again. Dr d theta is going to be 3 times the cosine of 3 theta, which again, when theta is pi over 4, ends up being 3 times the cosine of 3 pi over 4. But here, the cosine of 3 pi over 4 is negative root 2 over 2, so we get negative 3 root 2 over 2. Now, if you looked at the graph carefully, at pi over 4, what you should have found is that the distance was decreasing, or the curve was getting closer. Is getting closer. Now again, you might just say, well, oops, sorry about that. That's not a great surprise. The derivative dr d theta is negative there. Now let's keep doing it. Let's go with letter D apparently. How about letter C? All right, let's figure out what r of 5 pi over 12 is, right? Just shy of pi over 2, right? Just barely shy of that. So anyway, what would that be? That would be the sine of, what is that, 15 pi over 12? Well, that's confusing. How about the sine of, let's go with 5 pi over 4. And remember, that's in the third quadrant, so that's going to be negative root 2 over 2. All right, whatever. Dr d theta is going to be 3 times the cosine of 3 theta at pi over 12. Sorry, not pi over 12, but 5 pi over 12. That's going to be 3 times the cosine of 5 pi over 4. Again, I'm going to use my answer from last time to help me. Also negative, so we get negative root 3, or negative 3 times root 2 over 2. And now if you looked at the curve carefully, what you would find was that the distance increased, or curve got farther away. Curve got farther away. So it's not all about this. It's not all about that. In fact, you know, what was it all about? Let's clear this out. let's summarize what we saw. Okay, in sort of letter A, if you will, we had a radius that was root 2 over 2, and r prime that was 3 root 2 over 2, and a distance that was increasing. Part B, we had a radius which was root 2 over 2, and r prime which was negative 3 root 2 over 2, and the distance was decreasing. And letter C, even though it was listed as letter D, r was negative root 2 over 2, r prime was negative 3 root 2 over 2, and the distance was increasing. So what's going on here? And what I'm hoping is that it feels a little familiar, especially to my students. The phone is ringing. I'm going to have to pause the video right now. Okay, so we're back. Sorry about the little blip. Let's return and think about what's going on, right? We've got 3 cases. We really should have had a 4th case, right? I really should have had one where the radius was negative, but r prime was positive. If we had had that, by the way, if we had had a true letter D, oh, come on now. Haha. All right, turn my pen back on. There we go. All right, if we had had a true letter D, where the r, let's say, was negative, but r prime was positive, we would see that the distance would have been going down. So hopefully this feels familiar, right? It's all about the sign of r and the sign of r prime. So when r and dr d theta have the same sign, the distance, which parenthetically, by the way, is the absolute value of r, right, increases. And when r and dr d theta have different signs, then the distance, which is, again, the absolute value of r, decreases. What this should certainly remind you of is the 1D test for speed increasing and decreasing, right? And really, it's really the same test. It's like when v and dv dt have the same sign, then the absolute value of v increases. When v and dv dt have different signs, then the absolute value of v decreases. All right? So it's a very simple idea, but kind of cool. And if you really think about it, it makes a lot of sense. I'm going to clear out the text, try to talk about the hallway noise as it's the passing period here at Arlington. Write down what you need to. All right, here we go. So let's take a look at one application of this. It says, consider the limacon, which we're going to be studying as well, given by the equation r equals 1 plus 2 cosine theta. It says, using your graphing calculator and the window given, sketch the polar curve and indicate the direction of the curve. All right, so this is kind of cool. Why don't you pause the video now, take your calculator out, and sketch the curve. All right, let's take a look. So we're going to be studying limacons extensively in the next lesson. Here, I'll do my axes in red, and I will put my curve in blue, but it looks something like this. It kind of starts somewhere out here, and then it comes in, and does something like this. If we're going to put the direction on the curve, it looks something like this. Right. So there's our limacon. Letter B, find all values on the interval 0 to 2 pi where the curve passes through the origin. That's a neat question. Pause the video now and think about how you can find the angles where the curve passes through the origin. All right, did you figure it out? The curve is going to pass through the origin whenever its radius is equal to 0. So we literally are solving this problem. 1 plus 2 cosine theta equals 0, which means cosine theta, sorry about that, is equal to negative 1/2. Little trig curve remembering, or trig equation solving. My reference angle would be pi divided by 3, but since the cosine is negative, that means we're going to be in quadrant 2 and quadrant 3. So the angles will be 2 pi over 3 and 4 pi over 3. Is the curve's distance to the origin increasing or decreasing at theta equals pi over 2? Justify. Well, this is where we end up using what we just found out. So let's figure it out. Let's figure out what r of pi over 2 is. It's going to be easy enough. 1 plus 2 times the cosine of pi over 2. One of the things I like about that is that's equal to 0. So the radius is equal to 1. On the other hand, r prime of theta, right, a little bit of work here, is negative 2 times sine of theta. And if I want that at theta equals pi over 2, we'll get negative 2 times the sine of pi over 2. Love sine of pi over 2, it's equal to 1, so that's negative 2. Because these two have different signs, the distance is decreasing. Because r and r prime have opposite signs. Letter D is probably the hardest of them all. It says, give all values of theta on the interval 0 to 2 pi where the radius is increasing in length, where the absolute value of r is increasing, where the distance is increasing. Now we already know that's going to be locations, or those are going to be locations where r and r prime have the same sign. So to really be able to figure this out, what we need is we need number lines of r and r prime. All right, we're well on our way to getting a number line of r, and the reason why is that we already know, well, we know our endpoints, those are 0 and 2 pi, but we also know that r is 0 at 2 pi over 3 and at 4 pi over 3. So all we have to do is really test signs in here. We know that the radius is positive in here because we've tested pi over 2. If I chose some value in here, a good choice would be pi. What I would find is that the radius then would be negative. And if I chose some value in here, like 3 pi over 2, what I would find is that the radius would be positive. Sorry about that. So there's my radius. Now, what I'd like to do is I'd like to stack my r prime number line. It's just going to be easier to look at. Now, I have to be able to figure out where r prime is 0. Now, let's highlight r prime here for a second. Here it is. Here's our r prime. Right? Maybe take advantage of some space up here. If I'm solving this equation, negative 2 sine theta equals 0, right, that would give me sine theta equals 0, and theta would be angles like 0, pi, 2 pi, etc. So, going back to blue, the only place that we're really worried about it is pi. So we could take a value in here and test it, and it would be negative. We could take a value in here and test it, and it would be positive. All right, here we go. I'm looking for where the absolute value of r is increasing, where the distance is increasing. Well, at first it's not increasing, because what I've got is I've got opposite signs. But at some point in time, right in here, this thing stays negative, and this is negative, right? So I know that in this area, they're both negative. So from 2 pi over 3 all the way up to pi, they're both negative. Right? But there's also a location where they're both positive, right? That occurs from 4 pi over 3 all the way up to, but not including, 2 pi. Because in here, they're both positive. So that is all the angles. That interval contains all the angles where r and r prime have the same sign. All right? Kind of a nice analysis. And might I say, before I clear out the text, that if you go back to the curve, you can kind of get a sense for it. right? Because what's happening is all through here you're getting closer and closer to the origin, and at 2 pi over 3 you hit the origin. Then what happens is that the curve starts to go away from the origin, from 2/3 pi all the way to pi. And I know that seems weird to call that pi, but it is. Then what happens is from pi to 4 pi over 3 the distance is again decreasing, and then from 4 pi over 3 all the way to 2 pi we're getting farther and farther away from the origin. Okay. So for selected curves, you can really see that pretty well. All right. I'm going to clear out the text. Please feel free to clear it out or pause the video, write anything down you need to. All right, it's gone. Let's take a look. All right, that was our last problem. So that was really it in terms of polar calculus. There's a lot more that's interesting, things like second derivatives. You'll also in BC calculus or college level calculus, you'll work with the integral and integrating in polar coordinates. But for us, that's it. Our 2 last lessons on polar work are going to be really to look at some really beautiful polar curves and try to get some understanding of why polar curves work the way they work. All right. For now, let me remind you, this has been an Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.